Property of an angle bisector of a triangle. Theorem. The bisector of an angle of a triangle divides the side opposite to the angle in the ratio of the remaining sides. Given part, see here, in this triangle ACEB, ray CE is bisector of angle ACB. This is the given part. What is to prove? That this ray divides the side opposite to it in the ratio AE is to EB. This ratio should be equal to ratio of the remaining sides, that is CA is to CB. That means to prove is AE is to EB equal to CA is to CB. Construction is now, draw a line parallel to this ray CE through point B, which will intersect this extended AC in point D. See here. Construction is, draw a line parallel to ray CE passing through the point B, extend AC so that it intersect it at point D. Proof is, ray CE parallel to ray BD. See this, ray CE is parallel to ray BD. Therefore, we can say angle ACE equal to angle CDB. ACE equal to CDB. These are corresponding angles. Corresponding angles are congruent when lines are parallel. Now, taking BC as a transversal, we can have angle ECB and angle CBD as alternate angles. Alternate angles are always congruent when lines are parallel. But we have given that angle ACE is equal to angle ECB because ray CE is a bisector. From this number 1, number 2 and number 3, we can conclude that angle CBD equal to angle or congruent to angle CDB. See here, in the first statement, we have said that angle ACE is equal to angle D. In second statement, we are saying that angle ECB is equal to angle CBD. And in third statement, by given, we say that angle ACE is equal to angle ECB. Number 1, number 2 and number 3 statements give you conclusion that this angle D and this angle CBD is congruent. That is, angle CBD is congruent to angle CDB. Okay. Now we know that whenever in a triangle two angles are congruent, then side opposite to them are also congruent. Therefore, we can say that CD equal to CB. Okay, this is number 4. Now, in triangle ADB, this ray CE is parallel to this side BD. Therefore, by basic proportionality theorem, AC upon CD equal to AE upon EB, or AE upon EB equal to AC upon CD. See here. In place of this CD, now we can put CB here. Okay? Because we have already proved that CB equal to CD. Therefore, in place of CD, we can place CB by Roman 4. Once again, in short, we can prove this theorem like this. See here. We want to prove that AE upon EB equal to AC upon CB, where CE is the angle bisector. We will draw a line parallel to ray CE through point B, which will intersect AC in point D. Now, as the lines are parallel, these corresponding angles are congruent. Angle ACE is congruent to angle D. Similarly, as the lines are parallel, alternate angles are congruent, that is angle ECB is equal to angle CBD. But these two angles are already given as congruent because ray CE is a bisector. Angle ACE is congruent to angle ECB. By this 1, 2 and third statement, we can have this angle CDB is equal to angle CBD is congruent to angle CBD. If angles are congruent, then side opposite to them, that angle CBD, which side is opposite to that? Side CD. To angle D, opposite side is CB. Therefore, we can say that CD equal to CB. Okay. By basic proportionality theorem, that is CE is parallel to DB, therefore we can say that AE upon EB equal to AC upon CD. But already we have proved that CD equal to CB, therefore AE upon EB is equal to AC upon CD. In place of the CD, we can write here CB. Okay. If you are not understanding what are corresponding angles, then see this. These two are corresponding angles. These two are alternate angles. Corresponding angles, corresponding angles. Similarly, here also these two are corresponding angles. Okay. These two are also corresponding angles. Here, number 1, number 2. Here also, these are corresponding angles. Here, this and this is alternate angle. This is also alternate angles. Okay, no? So we should identify corresponding angles, alternate angles, and then we can find that theorem is very much easier. So we have proved that AE upon EB equal to AC upon CB. AE upon EB is equal to AC upon CB. Okay. Now, property of three parallel lines. If three lines are parallel, then we have to prove that AB upon BC equal to PQ upon QR. Okay. We will construct or we will draw this CP. It will intersect this BQ in point D. As in triangle ACP, AP is parallel to BD. Therefore, by basic proportionality theorem, we can say that AB upon BC equal to PD upon DC. See here. In triangle PCR, DQ is parallel to CR. It is given. Therefore, PD upon DC is equal to PQ upon QR. See here. AB upon BC is equal to PD upon DC. PD upon DC equal to PQ upon QR. Therefore, AB upon BC equal to PQ upon QR. Hence the proof. We want to prove that AB upon BC equal to PQ upon QR. In short, I can say AB upon BC equal to PD upon DC. By basic proportionality theorem, in this triangle, PD upon DC equal to PQ upon QR, and therefore AB upon BC equal to PQ upon QR. This property is known as property of three parallel lines and their intercepts. Now, practice set 1.2 given below. Ray PM is intersecting QR in some ratio, then we want to prove that PM is bisector of QPR. If it is bisector, then we will say that it is a bisector. If it is not, then we will say that it is not a bisector. For proving that, we will say QM upon MR equal to PQ upon PR. If it is possible, then and then only we can conclude that ray PM is bisector of angle QPR. Let us check the ratio QM upon MR. That is 3.5 upon 1.5. That is 35 upon 15. 5 sevens are 35, 5 threes are 15. So ratio is 7:3. Next ratio is PQ upon PR, which is also 7 upon 3. Here QM upon MR equal to PQ upon PR from 1 and 2. As this ratio is same, therefore ray PM is bisector of angle QPR by converse of angle bisector theorem. We can say that ray PM is a bisector of angle QPR. Roman 2. Here PM is intersecting RQ in the ratio 6:8. RM upon MQ is equal to 6:8. 2 3s are 6, 2 4s are 8. Here another ratio is ratio of remaining sides is PR upon PQ. It is 7 upon 10. From 1 and 2 we can say that ratios are not equal, and therefore by converse of angle bisector theorem, ray PM is not an angle bisector of RPQ. As ratio is not same, PM is not a bisector of angle RPQ. Third one, the ratio of QM upon MR. That is ratio made by the bisector. Ratio made by the ray, I will say, not the bisector. QM upon MR 3.6 upon 4. That is 36 upon 40. Multiplying both the numerator and denominator by 10. Okay, no? Or point shifts to the right. Therefore, we will give a 0 to this 4. That will 4 will become 40 in the denominator. 4 9s are 36. 4 10s are 40. PQ upon QR is also 9 upon 10. By Roman 1 and 2, both the ratios are equal, and therefore ray PM is a bisector of angle RPQ or QPR by converse of angle bisector theorem. The converse of angle bisector theorem is if the ratio made by the ray is equal to the ratio of the remaining sides, then we will say that the ray is a bisector of this angle QPR. Question number 2. Some values are given and we want to check that whether NM is parallel to RQ. NM, whether it is parallel to RQ. First of all, this PN is equal to PR minus NR. Because P dash N dash R, they are in a straight line. Therefore, we can say that Pn is equal to value of PR is given as 20 and value of NR is given as 8. 20 minus 8 equal to 12. MQ, see this MQ, it should be equal to PQ minus PM. PQ is given as 25 minus PM. It is 15. 25 minus 15. MQ value of MQ is 10. Now in triangle PRQ we will check this ratio PN upon NR. PN upon NR is 12 upon 8. 4 3s are 12. 4 2s are 8. And this PM upon MQ, putting the value of PM as 15, MQ value of MQ as 10, 5 3s are 15, 5 2s are 10. As both the ratios are equal, therefore we can say that PN upon NR is equal to PM upon MQ from 1 and 2. Therefore, by converse of basic proportionality theorem, we can say that segment NM is parallel to the side RQ. NM is parallel to RQ. Why it is? Because the ratio Pn upon Nr is equal to the ratio Pm upon Mq. Whenever we want to prove that Nm is parallel to Rq, then we should check the ratio of Pn upon Nr and the ratio of Pm upon Mq. If the ratios are equal, then and then only we can say that Nm is parallel to Rq. This is the converse of basic proportionality theorem. Third question. Values are given here and ray NQ is a bisector of angle MNP. Then by angle bisector theorem, ratio of MQ upon QP should be equal to ratio of remaining sides, that is NM upon NP. Okay, putting the values, we can have 2.5 upon QP equal to 5 upon 7, cross multiplying, then into 5 will become upon 5, 5 zeros are 0, then 2 will become 25, we will place point here, 5 5s are 25. Once again 5 zeros are 0, we will place a decimal sign here, it will become 25, 5 5s are 25. Now 5 7s are 35, that is 3.5 it will be. So value of QP is 3.5. Next question is question number 4. We want to prove that AP upon PB equal to AQ upon QC. AP upon PB will be equal to AQ upon QC if and only if PQ is parallel to QC. But PQ parallel to BC is not given. Then we will try to have that PQ is parallel to BC. As angle APQ and angle ABC are given as 60-60, they are the corresponding angles. As the corresponding angles are congruent, the lines are parallel. As PQ is parallel to BC, then we can apply the basic proportionality theorem. Then we can say that AP upon PB equal to AQ upon QC. Okay. See here in triangle ABC, PQ parallel to B. Here it is. Angle APQ equal to angle B equal to 60 degrees. See here. APQ equal to angle B, both are 60-60. It is given. But they are the corresponding angles. Oh no, when corresponding angles are congruent, then lines are parallel. Therefore, PQ is parallel to BC because of the corresponding angle test. What is corresponding angle test? If corresponding angle becomes congruent, then lines are parallel. Okay. Now, as PQ is parallel to BC, now we can say that AP upon PB equal to AQ upon QC. Okay, by basic proportionality theorem we have proved this. Okay, question number 6. 3 parallel lines are there given in a trapezium. It is given as a trapezium and we have given that 3 are parallel. Then by 3 parallel lines and their intercepts or their transversals property, that is AP upon PD equal to BQ upon QC it will be. Substituting the values, now 3 5s are 15, 3 4s are 12, should be equal to BQ upon 14. Cross multiplying we will have 5 into 14 equal to 4 into BQ. This into 4 will become upon 4. Now 2 2s are 4, 2 7s are 14. In the numerator now 7 into 5 will become 35 upon 2 it will be. 35 upon 2 is 17.5. So value of BQ is 17.5. We have solved this problem by using the property of 3 parallel lines and their transversal. What is that property? AP upon PD, see here, is equal to BQ upon QC. Now question number 6. Angle bisector is given. Then directly we can write by angle bisector theorem as MQ upon QP is equal to NM upon NP. See here, MQ upon QP is equal to MN upon NP. Substituting the value, 14 upon QP is equal to 25 upon 40. Here 5 5s are 25, 5 8s are 40. Cross multiplying, we will have 14 into 8 is equal to 5 into QP. 14 into 8 is 112, into 5 will become upon 5 now. See here 112 upon 5, 5 2s are 10, remains 1, it will become 12, 5 2s are 10, remains 2. We will have a point after decimal place. So 5 4s are 20 now. So answer is 22.4. Thank you. Thanks a lot. You can send this video to the needy students.